This is Chris Maynor again, coming to you from Union University, Jackson campus. In this problem, we are told that Janice Waller is the manager of the customer service department at First Bank of Jefferson County, and she can hire employees with either a high school diploma for $20,000 annually or employees with a bachelor's degree for $30,000. She wants to maximize the number of customers served given a fixed payroll. The following table shows how the total number of customers served varies with the number of employees. So, for example, if we hire, say, 4 high school diploma employees, 4 of them, then they will serve 370 customers. If Ms. Waller has a payroll of $160,000, how should she allocate this budget in order to maximize the number of customers served? This problem falls under the category of what we sometimes call a constrained optimization problem. You'll see that term in your textbook, constrained optimization. And the reason is for one thing, compared to some of the previous problems that we've looked at, this problem involves 2 decision variables. We've got employees with a high school diploma and employees with a bachelor's degree. So there are 2 decision variables. But more important, what really makes this a constrained optimization problem is the fact that we have a constraint. We have a payroll of $160,000. There's a budget, and this limits what Janice Waller can do. She can't just hire 20 employees with a bachelor's degree. She can't afford it. Her payroll limits what she can do. So what we would like to do is to determine how many of each type of employee, those with high school degrees, those with college degrees, how many should we hire in order to maximize the total number of customers served. Well, to do that, we first remember that we make decisions at the margin. So for each type of employee, the first thing I want to do is to calculate a marginal benefit. The marginal benefit of the first high school employee is $120. That's, of course, if we're assuming that with 0 employees there would be 0 customers served. The second high school diploma employee adds an additional 100 customers served. The third adds an additional 80. And if we go over to the bachelor's side, the marginal benefit would be 190 and 80. I move to the next slide, and you see that I've computed all of the marginal benefits for high school diploma employees and marginal benefit for bachelor's degree employees. Now, what do we do now? Well, remember Jane, Joe, and Joan, the previous problem. How did we determine which individual to hire first? Not by looking at the number of the amount of sales they generate, but the amount of sales generated per dollar spent. We want to do the same thing here. It's not just a matter of hiring the employee with the greatest marginal benefit. We want to hire the employee that has the greatest marginal benefit per dollar. So I'm going to begin with the high school diploma employees and take each marginal benefit and divide by their salary, what we would have to pay that individual. So high school diploma employees are paid $20,000 a year. I'm sorry for that mess there, but it's $20,000. And for the bachelor's degree, we would divide their marginal benefit by their $30,000 salary. That looks a little bit better. And so, moving to the next slide, I've gone through all the calculations. Now you'll notice that I did not divide by 20,000 and 30,000. That would get a little bit messy. We'd start to have some decimals, but I was consistent. I divided the marginal benefit of high school employees by 20 and the marginal benefit of bachelor's degree employees by 30. And what we get is marginal benefit per dollar spent for each additional employee. So now we're ready to start hiring workers. Janice is now ready to start making her decision. She has a $160,000 budget. We don't want to go over budget. We don't want to go under budget. So who should we hire first? Well, we're going to hire the employee that gives us the highest, the greatest bang per buck, the greatest marginal benefit per dollar. That would be the first high school diploma employee with a six customers served per dollar spent. Then we would hire another high school diploma employee. Notice that we're not going to hire that first bachelor's degree employee yet. 5, let me mark this, 5 is greater than 3.3. So next on our hiring list would be the third high school diploma worker. 4, again, is greater than 3.3. Our fourth hire, again, would be another high school diploma employee. Now we compare the fifth high school employee with the first bachelor's degree employee. What should we do? Well, we should spend the next dollar on this first bachelor's degree. Okay, so notice we go from 6, 5, 4, 3.5 to 3.3. Now we have sort of an interesting situation. Now we compare the fifth high school employee with the second bachelor's degree employee. They have an equal employees served per dollar spent. So what do? Well, we flip a coin. Maybe we hire the second bachelor's degree and then turn around and hire the fifth high school employee. But notice now, we're at 5 high school diploma employees, and we are at 2 bachelor's degree. 5 high school, remember each one has a salary of $20,000. Each bachelor's degree has a salary of $30,000. We're now at our $160,000 budget. We can't go over budget. We don't want to go under budget. So what are we going to do? What should Janice Waller do? Well, she should hire 5 high school diploma employees and 2 bachelor, we say they have a BA degree, and that will satisfy our budget and maximize the number of customers served. Now notice something. Notice that when we reach what we might call equilibrium, when we reach that point of optimization, that the marginal benefit per dollar spent is equal for high school employees and bachelor's employees. Well, that leads us to a very important principle. We've already seen the profit maximization rule. Well, here's what I call the equimarginal principle. This applies to those constrained optimization problems where there's more than one decision variable and there's a constraint, a budget, a limit imposed on the decision maker. To maximize total benefits subject to a constraint on the levels of activities, we're going to choose the level of activity so that the marginal benefit per dollar spent is equal for all activities. And so if there are, say, A through Z choice variables, A through Z decision variables, then we would want the marginal benefit per dollar spent for activity A to equal the marginal utility per dollar spent for activity B, C, and so on. But remember, at the same time, we want the chosen level of activities to satisfy our constraint. We don't want to be under budget, and at the same time, we can't go over budget. So, again, this is an example of a constrained optimization problem, and we use what I call the equimarginal principle.